imagine for a second that you just hired a new research assistant.
Okay.
And this person is, brilliant, lightning fast.
Yeah.
And they speak to you with this absolute unwavering confidence.
Right. Sounds like a dream hire.
Exactly.
Yeah.
Sounds like an incredible asset to have, right? But after a few weeks of working together, you start to get this sinking feeling.
Uh-oh.
Yeah, you realize you have absolutely no way to know if they're actually doing the fresh, real-time research you asked for, or if they're just confidently reciting an outdated Wikipedia page that they, memorized 3 years ago.
That is a very real problem.
Right. You'd obviously want to test them.
Yeah.
But how do you meaningfully test an entity that has essentially memorized the entire public library?
You really can't. Not easily anyway.
Which brings us to today. Welcome to the Deep Dive. Today, we are exploring this really fascinating new research paper titled DR Arena, an automated evaluation framework for deep research agents.
It is, it's a truly critical piece of research for anyone incorporating these AI tools into their daily workflow, because right now we are increasingly relying on large language models, specifically these newer deep research agents, to do our heavy lifting.
Oh, absolutely.
We ask them to synthesize complex market reports or prep us for critical meetings, map out industry trends, things like that.
Yeah, the stakes are getting high.
Exactly. But figuring out if they are actually good at live investigation rather than just, sounding smart, well, that's become a massive bottleneck for the entire technology sector.
And the mission for our deep dive today is to explore how scientists are attempting to solve this. They're building what is essentially an automated, ruthless combat arena to test the true capabilities of these AI research agents.
It really is a combat arena.
It is. And we're going to look at the mechanics of how this arena functions, what actually happens when the world's most advanced AIs are thrown into the ring, and most importantly, what this means for you, the listener, whenever you rely on these tools to get smart fast. Okay, let's unpack this. We know testing AI is important, but why do we need a whole new arena? What is fundamentally failing with the current way we test these models?
Well, the core issue is that current AI benchmarks are what the researchers call static.
Meaning they don't change.
Exactly. They are fixed data sets, just a set list of questions and answers. And relying on static tests in a dynamic world, it creates 3 fatal flaws.
Okay, what's the first one?
First, they have very limited task generality.
Right.
They usually test these rigid, predefined patterns of investigation that they don't map well to the messy, unstructured reality of navigating the live internet.
Yeah, the internet is not a multiple choice test.
No, it's really not. And second, there is what they call temporal misalignment.
Temporal misalignment.
Basically, the world constantly changes and facts update, right?
Right.
But a static test remains entirely frozen in time.
Right. So if an AI agent goes out today, finds the actual current truth about, I don't know, a company's stock price or a new scientific discovery.
It gets penalized.
Wow. So it might get marked wrong simply because the test's answer key was written last year.
Precisely. The system penalizes the AI for being accurate to the present day.
That's wild.
It is. But the third, and perhaps most fatal flaw, is data contamination.
Ah, okay.
These static tests, like the standard reading comprehension or math benchmarks you always hear about in the news, they've been sitting on the internet for years.
Right. Anyone can download them.
Right. And because the newer AI models are trained by essentially scraping the entire web, those tests have been swept up into their massive training data sets.
So they've already seen the test.
Exactly. The AI has already read the test before it even takes it.
Oh, man. It's like a student studying for a geography test by managing to steal and memorize the answer key from 1989.
That's exactly it.
When the teacher asks a question about the Soviet Union, the student spouts off the exact right answer according to that old rubric, and they get an A+ on the test, but they completely fail reality.
That captures the essence of it perfectly, though the paper does draw a slightly more technical distinction.
Okay, how so?
The researchers differentiate between parametric memorization and genuine reasoning.
Parametric memorization.
Yeah. When a model reads a benchmark during its training, it adjusts its internal weights, its parameters, to map the question directly to the answer.
Like a reflex.
Exactly. It's a reflex, muscle memory. It isn't reading the question, understanding the context, formulating a research plan, and then deducing the answer.
It's just pattern matching.
Just pattern matching. And for you listening, this really matters because When you asked an AI for a real-time brief on a competitor, you don't want a reflex based on old data.
No, you want active, live, intelligent investigation.
Exactly.
But wait, if the internet is constantly being vacuumed up into these training sets, how do we possibly build a test that avoids that contamination? Do we just have to, like, write a brand new test by hand every single morning?
Well, human engineers couldn't possibly keep up with that pace.
Right, that would be impossible.
So the researchers behind DR Arena engineered an automated workaround. They call it a dynamic information tree.
Okay, how does that work?
Instead of a human writing the test, the system utilizes an automated AI judge, which they call the examiner.
The examiner.
Right. The examiner wakes up, checks a live data stream like Google Trends to see what topics are currently relevant today.
Okay.
Then it selects a live website, and it scrapes it to build a fresh, brand new tree of facts.
Oh, wow.
Yeah. Because the test is generated on the fly from the live web, it is physically impossible for the AI agents taking the test to have memorized the answer key.
Wait, if the examiner's just dropping these AI agents onto the open web, aren't we just testing their ability to use a search engine rather than their ability to actually reason?
That's a good question.
Because if they don't have the context provided to them, it feels like a different kind of test entirely.
It is a different kind of test, and that's exactly the point. The paper establishes a strict rule called complete decontextualization.
Complete decontextualization.
Yeah.
Meaning what?
Meaning, the AI taking the test is never told what specific website the examiner used to build the tree.
Oh, I see.
If you hand an AI a specific URL and ask a question about it, you are really only testing reading comprehension.
Right.
By forcing the AI to start from a blank slate on the open web, you test its ability to autonomously formulate search queries, sift through irrelevant results, cross-reference sources, and actually synthesize data.
That is way harder.
Much harder. And to evaluate this rigorously, the examiner tests two distinct dimensions, depth and width.
So it doesn't just read one page, it builds a web of connections.
Yeah.
How does it isolate those two dimensions in a single search task?
Let's look at a specific example from the paper. They used one regarding late 1980s video game consoles.
Okay, I like that.
A static test would just ask, when did the Game Boy come out?
Right. Simple fact retrieval.
Exactly. The examiner, however, creates a dynamic task from its information tree. To test depth, which requires multi-hop logical reasoning, the examiner masks the target entity entirely.
It hides the Game Boy.
Yes. The prompt asks the agents to identify the 1989 console designed by the creator of the Game & Watch series.
Ah. So the AI first has to search for the creator of Game & Watch.
Right.
Figure out who that person is, and then run a secondary search to find out what console that specific person designed in 1989. It forces a chain of logic.
Exactly. The AI has to discover that Gunpei Yokoi created Game & Watch,
Okay.
and then determine that Yokoi designed the Nintendo Game Boy in 1989.
Got it.
If the logic chain breaks anywhere along that path, the model fails. That is the test of depth.
Okay, and what about width?
Width is all about information gathering and aggregation.
Right.
So once the agent identifies the Game Boy, the second half of the prompt requires it to compare its battery requirements and screen technology against the Atari Lynx and the Sega Game Gear.
Oh man, that's a lot of separate pieces of data.
Exactly. Now the AI has to branch out, run parallel searches, and aggregate scattered facts. It has to find that the Game Boy took 4 AA batteries with a non-backlit screen,
Right, I remember that.
while the competitors required 6 AAs and featured backlit color screens.
Okay, so the test is administered. The AI goes out, it hunts down the logic, gathers the details, and comes back. But evaluating that output can't be as simple as just checking a box.
It's definitely not.
How does the examiner actually grade these complex narrative responses?
The agents enter what the researchers call the Adaptive Evolvement Loop.
The Adaptive Evolvement Loop.
Yeah. The examiner takes 2 different AI models, say, one from Google and one from OpenAI, and gives them the same dynamic task.
Like a head-to-head battle.
Exactly.
Okay.
When they return their answers, the examiner uses a highly specific checklist generated from that initial information tree,
Okay.
and it diagnoses any failures into specific categories. Did the agent suffer a deep failure?
Meaning?
Meaning, did it break the logic chain and confidently retrieve information about the wrong console entirely?
Right, like if it thought Sega Genesis was the answer.
Exactly. Or did it suffer a wide failure? Meaning, it correctly identified the Game Boy, but it missed the specific detail about the 6 AA batteries for the Lynx.
Gotcha.
It could also fail both or none.
Here's where it gets really interesting. Because if both of these top-tier models come back and they both perfectly identify the Game Boy and they both get all the battery specs right, the system doesn't just call it a tie and move on. It triggers a pressure test.
That's right.
It acts exactly like a smart video game that automatically scales the difficulty based on your skill level.
It actively intervenes. A high-quality tie signals to the examiner that the task was simply too easy for these specific models.
Okay, so what does it do?
In the next round of the tournament, the examiner automatically increases both the depth and the width requirements.
Oh.
It dives deeper into the information tree to generate a more obscure, complex logic chain, and it demands a wider net of specific details.
And it just keeps going.
It will keep doing this, round after round, until one of the models finally cracks under the cognitive load.
That is ruthless. But if the system keeps scaling up the difficulty like that, do some models just get stuck in a loop of tying over and over?
Actually, the researchers found a fascinating correlation regarding exactly that.
Oh.
Yeah. When they pitted highly divergent models against each other, meaning models with very different underlying architectures and skill levels, the matches usually ended in under 2 rounds.
Okay, that makes sense.
The system throws a hard constraint, the stronger model handles it, and the weaker one shatters immediately.
Right.
But the anomaly occurred when pitting OpenAI's GPT-5.1 search against its sibling model, O3 search.
Because they are built by the same company.
Because they share similar training DNA and underlying neural architectures.
Oh, I see.
The researchers call this behavioral homogeneity. Even though one model might technically be more advanced, their internal reasoning processes are so similar that they share the exact same blind spots.
Oh, wow. So they fail in the same way.
Exactly. When faced with a pressure test, they would often fail in the exact same way, leading to more ties.
That's crazy.
The examiner had to work incredibly hard, scaling up the complexity over an average of 3 or more investigation rounds, just to find a subtle enough difference in their long horizon synthesis to declare a winner.
So the arena is fully operational. We have dynamic trees, we have decontextualized prompting, and adaptive pressure tests.
Right.
When they ran the tournament with the world's best models, did the results actually align with reality?
The results were a massive validation for the framework. DR Arena achieved a 0.94 Spearman correlation with the LMSYS Search Arena leaderboard.
And that leaderboard is the human-voted one.
Exactly. It's a massive benchmark driven by thousands of human voters.
A 0.94 correlation means it is essentially perfectly mimicking what thousands of human professionals prefer.
Yes.
But it's doing it automatically, instantly, and without the human labor cost. That is incredible.
It is. And while it was doing that, older static tests were scoring negative correlations, like Future Search at negative 0.90.
Negative.
Yeah, those old tests were actively penalizing the best models for finding current information.
That's so broken.
Totally broken. But beyond just validating the leaderboard, the arena's detailed diagnostics revealed distinct cognitive profiles for the top-tier models.
Oh, because we aren't just looking at a final score. We can see exactly how these models fail.
Precisely.
This is hugely practical for anyone listening who uses these tools daily.
Yes, it is.
Let's break down those profiles, starting with GPT 5.1 search.
Well, the framework identified GPT 5.1 search as the most robust, balanced model.
Okay.
It had the lowest overall failure rate in the tournament, hovering around 50%.
Still 50%. Wow.
Right, these are hard tests. But more importantly, its errors were symmetrical. It didn't have a glaring structural bottleneck. It failed equally on deep logic and wide coverage as the difficulty scaled up.
So it's a good all-rounder. Then there's a model like O3 Search, which is engineered differently. The data paints it as heavily biased toward logic, right?
Yes, O3 Search is designed with a heavy emphasis on reasoning pathways. And the data shows it. It had the absolute lowest deep failure rate at only 19%.
Wow, 19% is really good.
It is. If you have a complex multi-hop logical deduction, O3 is incredibly reliable. But it struggles significantly with wide coverage.
Why is that?
Because its architecture spends so much computational power, so many internal tokens going down deep rabbit holes to ensure the logic is perfect, that it tends to get tunnel vision.
Ah, I do that sometimes.
Right. It loses the broader context and frequently misses the scattered, wide-net details requested in the prompt.
Which is the exact inverse of models like Perplexity, Sonar Pro, or Grok 4.
Correct. Those models are built heavily around retrieval-augmented generation, or AGE architecture.
Right, yeah.
They are essentially supercharged search engines. They are fantastic at casting a wide net, vacuuming up paragraphs from a dozen different websites, and aggregating that data.
They win on width.
Big time. But because they're optimized for chunk matching rather than deep internal deduction, they suffer from high deep failure rates. They will often retrieve a massive amount of highly accurate data about the completely wrong target entity because they failed the initial logic puzzle.
Oh, that's dangerous. So to put this to work for you listening, if you are using these tools to prep for an important meeting, you need to adjust your review process based on the tool you chose.
Absolutely.
If you use a reasoning-heavy model like O3, you need to manually double-check that it didn't miss a key bullet point on page 4 of the financial report because it got, obsessed with a logic chain on page 1.
Exactly.
But if you use an info gatherer like Perplexity, you really need to scrutinize its underlying logic. Don't just assume that the beautiful, comprehensive summary it generated is actually about the correct competitor.
What's fascinating here is that this exact tension, the tension between producing a comprehensive, beautiful summary and actually being factually correct, revealed a major flaw in how humans evaluate AI.
Really?
Yeah. The researchers refer to it as the factuality fluency trade-off.
The factuality fluency trade-off.
Okay. Even though DR Arena aligns closely with human preference overall, the automated examiner caught a critical vulnerability that human voters completely missed.
Let's look at the specific match trace from the paper between Claude Opus 4.1 and Perplexity Sonar Pro.
Okay.
The models were given a task about labor statistics, specifically requiring them to pull live data from the 2024 Occupational Outlook Handbook to find occupations with higher median wages than software developers.
Right. So Claude returns its answer, and it produces a beautiful, flowing, highly analytical narrative.
Classic Claude.
Exactly. It uses sophisticated phrasing and transitions. It reads exactly like an executive summary written by a top-tier consultant.
Sounds great.
But the automated examiner flagged it for a severe hallucination.
Oh.
Claude cited the median pay for managers as $169,510, which was likely an outdated figure from 2023 instead of the correct live 2024 figure of $171,200.
Just completely made up the wrong number.
Or relied on an old one. Yeah. Furthermore, it incorrectly included database architects in its list, which violated the specific occupational grouping logic established in the source text.
Yikes. Meanwhile, Perplexity's response was entirely different in tone.
Very different. Perplexity delivered a very dry, structured, data-centric, bulleted list. It was frankly boring to read.
Yeah.
But according to the live 2024 data scraped by the examiner, it was 100% factually perfect.
And this highlights a fundamental vulnerability in human nature.
It really does.
When human evaluators look at these two outputs side by side, they consistently rank Claude higher.
Yep.
We conflate eloquence with accuracy. If it sounds confident and uses good grammar, we just assume the underlying math is right.
The mechanism behind this is inherent to how large language models work. They are, at their core, prediction engines trying to generate the next most plausible word.
Right.
When a model like Claude is optimized heavily for conversational fluency, its neural network prioritizes a smooth narrative flow.
So it wants to sound good.
Exactly. Sometimes the mathematical probability of generating a fluent-sounding word, like an outdated but heavily discussed salary figure from its training data, it overpowers the strict constraints of the factual data it just retrieved.
Wow.
The drive to sound good overrides the grounding.
But the automated examiner in DR Arena doesn't care about beautiful prose.
Not at all.
It rigidly checks the grounded rubric, penalizes Claude for the hallucination, and awards the win to the boring, accurate Perplexity.
Right. It acts as an unblinking factuality auditor.
That's a great term.
It proves that as these models become increasingly sophisticated at mimicking human eloquence, human evaluators actually become less reliable.
We get tricked.
We do. We are too easily swayed by good prose, meaning we need automated, logic-bound systems to act as a backstop.
That makes perfect sense, but it leads to a rather glaring question.
Okay, lay it on me.
We are relying on the AI examiner to be this unblinking auditor. But the examiner itself is just another large language model. It has its own neural network. It has its own training data. What happens when the judge gets an ego? What happens when the model's internal memory clashes with the facts it just scraped from the live web?
That is the primary limitation the researchers highlight, a phenomenon they call the double-edged sword of parametric bias.
Parametric bias.
Yeah. The judge is instructed to strictly evaluate the agents based purely on the information tree it scraped.
Right.
But sometimes its own massive pre-trained memory, its parametric weights, overrides those instructions.
Can you walk us through how that actually breaks a test in practice?
Sure. The paper details a test built around a historical best game ever contest held by the website Game FAQs.
Oh, I remember that site.
Yeah.
Yeah.
So the live web scraping correctly built a rubric establishing that the 2005 winner was the game Final Fantasy VII.
Right.
One of the AI agents successfully navigated the web and returned that exact correct answer.
Good for the agent.
But the examiner, drawing on its own internal biased memory, hallucinated. It confused the 2005 contest with the 2009 contest.
Oh, no.
Yeah. It stubbornly insisted that the winner was Ocarina of Time, and it unfairly penalized the agent that had actually found the ground truth.
It's like the ultimate confident but wrong middle manager.
Yes.
It has the correct report sitting right on its desk, but it ignores it because it thinks it already knows the answer.
Exactly. The pre-trained weights overpowered the context window. However, the researchers emphasized that this parametric bias is a double-edged sword for a reason.
Meaning there's a good side.
Yes. Sometimes that internal ego actually saves the framework from its own automated mistakes.
How so?
In a different test regarding a 2007 Game FAQ's character battle, the automated scraping process actually made an error.
The scraper messed up.
Right. It built a flawed rubric that incorrectly listed the character Link as the historical runner-up.
Okay.
The examiner received this flawed answer key, but drawing on its vast pre-trained knowledge of internet history, the examiner's internal neural network realized the rubric was factually incorrect.
Wait, it knew the test was wrong.
Yes. It actively overrode its own core instructions, ignored the bad data in the context window, and correctly awarded the win to the agent that identified the true historical runner-up, which was CloudStrife.
That is wild. So the judge's internal knowledge can hallucinate and ruin a perfectly good test, or it can spot a flawed test and prevent an unfair penalty.
Exactly.
It introduces an element of unpredictability into an otherwise rigid system. So what does this all mean?
Well, it means that the era of evaluating AI with a simple pop quiz is well and truly over.
Yeah, clearly.
We can no longer hand an AI a static sheet of questions and assume a high score equates to functional intelligence in the real world.
Right.
The DR Arena framework demonstrates that to truly understand the capabilities of these models, we have to throw them into a dynamic, live web environment.
We have to pressure test them.
Exactly. We have to force them to navigate decontextualized data, subject them to adaptive pressure tests, and ruthlessly probe their specific architectural weaknesses in both logical depth and information width.
And for you, as the end user integrating these deep research agents into your life, the big takeaway is to start approaching your own AI interactions the exact way the examiner does.
Right.
Don't sit back and accept a beautifully written answer just because it flows well. You have to actively interrogate the output. Look for the depth. Does the underlying logic actually track from point A to point B?
Yes.
And look for the width. Is the data set complete? Or did the architecture get tunnel vision and miss the broader context? Until these systems are flawless, you have to be your own examiner.
Because as these tools become more deeply embedded in our critical decision-making processes, the ultimate responsibility for verifying the truth still rests entirely on human shoulders.
Yeah.
The AI can gather, it can synthesize, and it can reason, but critical verification is still a human requirement.
Which leaves us with one final, slightly unsettling thought to chew on before we go.
Okay.
As dynamic frameworks like DR Arena become the new gold standard for the industry, we are explicitly relying on highly advanced AI models to grade and evaluate other highly advanced AI models.
Right.
If human engineers are no longer fast enough or capable enough to write the tests and evaluate the complex reasoning pathways of these deep research agents, how do we ensure the very concept of ground truth doesn't eventually just become whatever the majority of AI models happen to statistically agree on?
Wow.
As we automate the evaluation of knowledge, are we slowly cutting ourselves out of the loop of defining what is actually true?
That might be the most important epistemological question of the next decade.
Thank you so much for joining us on this deep dive. Keep questioning the information around you, don't fall for the beautiful lies, and we will see you next time.